Okay, so now I'm approaching to almost the. I have only two more parts to tell you, two more objects to define. Yeah, so, and I guess we'll be done with what was promised. Okay, so there is also some, I will change the topic completely, because in this moment I was telling you how to generate new spaces from using old ones, right? But now I will tell you something about the separation axioms. Just to give you an intuition. Just to give you an intuition. Yeah, I've seen it in the internet, an illustration how to speak about the separation axioms. So, for example, you have imagine you have a shooter, a person that is aiming at the target and shooting, and from a very distant point of view, this person, for example, sees 3 points. Right? And this shooter can distinguish between those 3 points. Okay? So he or she can see this point, this point, this point, and can aim at a chosen point out of those 3 and shoot. And in topological, to express it in topological way, one could say that there is an open set from the topology that we choose that enables the shooter to distinguish those points. So for example, he or she can choose 2 open sets, and one open set that contains this point and does not contain this point, and another set that contains this point but does not contain this point. And by using those 2 sets, he or she can separate them, aim, shoot, and hit. Yeah? And also he or she can distinguish between this point and this point. Yeah? And this point and this point. And in some sense, this gives us a rich topology. Yeah? Why? Because we have like three objects. And we can think that we have 3 open sets. Every of these points create an open set. So also, if we can distinguish those 2 points, we can also distinguish between the group of those 2 points and the 3rd point. And we can also distinguish between the group of those 2 points and this point. And we can also distinguish between those 2 points and the point in the middle. Yeah? And we can also aim at all 3 points and not distinguish them. It's up to us. Yeah? We have to, so to speak, full knowledge about our aim. Yeah? We can choose whatever we want because we are good shooters. But now imagine that this person got a beer or 2, and the image is not that clear anymore. Yeah? So he or she sees 3 points somehow in a fuzzy way and can distinguish this point from this point, but cannot distinguish this point from this point. Okay? So for example, he or she can distinguish this point, he or she can distinguish this, and can distinguish this, but cannot distinguish between those 2 because had drunk too much beer. Yeah? And also he or she can distinguish, not distinguish, so he or she can treat the whole thing as one. Yeah? And also after another beer, he or she cannot distinguish anymore between those 3 points and sees only everything as one target, right? So that's another situation. And it also shows us how somehow what it changes when we have richer or poorer topology. In this sense, we can, from philosophical point of view, having such a rich topology, we can speak about every object separately. We can distinguish them. In this situation, our language, topological language, is too poor to distinguish objects. So we can only say about everything or nothing. And from the topological point of view, in topology, we say about the separation axioms, which certain topologies fulfill or not fulfill. So certain topologies are richer and fulfill more separation axioms, providing us better tool to distinguish between objects. And some topologies are poorer, do not fulfill these separation axioms, and in this sense, they are, let's say, not precise enough. Yeah? And let me start with something which is very basic, basic situation in topology, which is many spaces that are being under consideration in topology are so-called Hausdorff spaces. And let me give you the definition of Hausdorff space. So X is a Hausdorff topological space if for every 2 points A and B in X, there are neighborhoods this different points, so A is not equal B. Okay? There are neighborhoods N containing A and M containing B such that N and M is the intersection of N and M is empty. Yeah? So what it means that if we have a Hausdorff space and we have 2 points here, then we will find 2 open sets like this and like this, for example, which contain those 2 objects. One contains only one of these and the other contains the other one. And these sets, these neighborhoods are open these are neighborhoods. So these sets are disjoint, and which are when they are neighborhoods. When we say that they are neighborhoods, as we defined it before, it means that they contain some open sets containing those points. Yeah. So it means that if they are neighborhoods, it means that there is a open set containing this point and open set containing this point included in these neighborhoods. So what it means is that this intuition that I gave you before, it means that we can separate those points using open sets. So our topology is rich enough to speak about this reality, this space, in such a way that distinguishes those 2 points by the terms of topology. Yeah, and there are also other axioms. This axiom is also sometimes called T2. That's another notation for this axiom.
But what is the axiom?
Excuse me?
What is the axiom?
Okay, a topological space fulfills the T2 axiom if it has this property, this Hausdorff property.
So it's a definition, not
an
axiom.
Yeah. Yes.
this might be stupid, but why do we talk about neighborhoods instead of just saying there exist these sets?
Doesn't matter.
Oh.
It's the same. It's the same. Okay. Yeah, and there are many various axioms, separation axioms, and I don't want to mention all of them because I don't even know which one are going to be used by the speakers tomorrow and the day after tomorrow, etc. So I will give you just two more examples of those axioms. So axiom T3 says that so a space X, topological space, has, let's say, has T3 if A, it is a Hausdorff space which means that you can distinguish 2 points by the means of the topology. And second, for every A from the space and F closed set in X, there exists N containing X and M containing F, these are neighborhoods, such that N and M are disjoint. Okay? So what it basically says is that if we have a space, and in this space we have a point, and we have a closed set, then those two objects can be distinguished by the means of neighborhoods, yeah? Of topology. Seems to be quite similar to the previous definition, but it makes difference. Yeah? But we would need to have exotic examples to show you why it makes a difference. But it's all about the same intuition. So we want our topology to be rich enough to describe our reality in a way which enables us to distinguish points from closed sets. Okay. And maybe I won't write the whole new definition here, but I will just write here that T4 property means that the above condition is fulfilled after replacing A with another closed set. So a space is T4 if we not only can distinguish point between point and point, not only can distinguish between point and a closed set, but also can distinguish between two closed sets. Yeah? Then it's T4. Actually, as I said, I don't know if you will see the application of this terminology, but even if not, then please remember about the example with the shooter. Yeah, that it somehow shows what is the intuition behind it. Yeah? That we want, as I said again and again and again, we want to have a language rich enough to distinguish between objects.
Shouldn't there be that M contains A small in the previous definition?
Where? Here?
Here, in the beginning. N contains A, not E.
Yeah, excuse me, yes, A. Thank you. All right. Do you have any questions regarding this?
I have a question.
Yep.
Is do those definitions fulfill the notion of the regular and normal?
Yeah, exactly. So this definition T4 is exactly something which is also called the normality condition. Yeah? So a space is normal. We say that a space is normal when it fulfills the T4 condition. And it is, as far as I remember, it is regular if it fulfills T3. That's just another terminology.
There is no standard agreement. Sometimes it is required that normal is T4 plus T1 or something like that.
Yeah.
You will find different definitions in different books.
I see. But that's how I was taught. Yep.
Just a funny remark on this shooter example.
Yeah.
There's a famous mathematician, Scott, who invented the Scott topology. And there is another topology called sober topology. And somebody wrote a paper, Scott is not always sober.
Many words from common usual language have different meaning in mathematics. Yeah, actually, yeah. Like ring or body or group or witness, all those words have different meanings in the field of mathematics. Yeah. All right. So maybe because I think it would be nice to have a little time at the end to discuss some philosophical consequences of what I said. Maybe you will have some general remarks or questions, not technical ones. But before that, one more important notion from topology, which is compactness. Compactness, and this will be the final thing that I will speak about here. So, let's say, do you all know what is a sequence and what does it mean that a sequence is convergent? No. Okay. So let's say that compactness. So what is compactness? It's somehow we would like to have a notion that would describe a situation where a given set is bounded and closed, and we would like to have it in a very general setting. And this intuition that a set is closed means that if you have, let's get back to this intuition that we have like like a disk which has its boundary, right? And the intuition is that if we have, maybe I'll first explain what is a sequence and convergence of a sequence. So let's say we have AN. It is a sequence, and for all n, AN belongs to a space X. Okay? Which means that we have, it's another notation for such an object, okay? That we have infinite number of elements from the space X, and we numerate these numbers using natural numbers. Okay? So it's the first one, second, third, fourth, and etc. etc. Actually, there should be also A0. A0, A1, A2, A3. That's the sequence. And what it means that the sequence is convergent, I could give a general definition using neighborhoods, but I prefer to give you a definition using distance function. Okay, so let's assume that D is a distance function in X, the one that I was talking about in the beginning. So a function that measures distances between points. Okay? Then we say definition. We say that AN is convergent to G. There is a point, some point in the space X, when for every epsilon bigger than 0, there is n from a natural number n such that distance between xn and g is smaller than epsilon for all n bigger than n. Okay? And what it means, let's draw a picture. Let's draw a bigger space. Let's say this is a space X, okay? And we have a sequence of elements. There's 1, 2, 3, 4, 5, 6, right? And it can happen that, let's say intuitively, this sequence can be convergent, which means that those points start to accumulate around certain point of this space. How we can see that? For example, that the next points are looking like this. So they are closer and closer to a certain point here. Okay? So they start to be somehow separated, but the further we go, the closer we are to a certain point. It looks like this sequence is converging to a point here. Okay? That's the intuition. And we describe this intuition using this way. And it means that here is some point G, this point G, such that if we draw a ball, a disk around G of a radius epsilon, if we draw such a disk, then we can find such a number n that all the elements from this sequence that have bigger index than n are inside this ball. So maybe there are some points which are outside this ball, but after we reach certain index, certain number, all the remaining points will be inside this ball. It might be a very big number, like 5 million, but it's working.
But it's a good remark, I think, to say that there can only be finitely many points beyond the disk.
Yeah.
This is the clue. Then this is the point.
Yeah.
That only finite, whatever small ball you take, only finitely many is beyond it.
That's true. Yeah. You can express it like that. That for every ball around G, there is only finite number of elements from this sequence which are outside. Because let's say there is infinite number of points outside this ball, then we wouldn't be able to find such an n, because for every n there would be a higher natural number, such that the element with this index n would be outside of this ball. Yes? So that's the convergent sequence. And just to give you some examples of convergent sequences, let's imagine a sequence of this form. Yeah, so an equals 1 plus 1 divided by n. Okay? This is a sequence. And how it looks like. A1 is 1 plus, we put 1 in place of n, so it's 1 plus 1 divided by 1, which gives us 2, right? Then A2 is 1 plus 1 over 2, gives us 1 half. And then, okay, so can you guess what is the limit of this sequence where it converges? 1. Very well. So it becomes smaller and smaller and smaller, and finally we get to the point where it's very close to 1. However, no element from this sequence equals 1. Yeah? So we have a sequence which is convergent to 1, but it never reaches this 1. Yeah? Is it clear? Yeah?
Can I have a question?
Yeah, sure.
But if we consider as the one that goes to infinity, then the last element would be infinity, wouldn't it?
Infinity does not belong to the set of real numbers, for example. Yeah? So it depends. For example, if we have a sequence, an equals n, okay? It looks like that. 1, 2, 3, etc. Right? So it goes somehow to infinity. And now the question is, in which space we consider it? If we are in natural numbers, if we are in this space, then we say that infinity is not a natural number. It's not a natural number, so this sequence is not convergent at all. But if we consider the same example in the following space, then it is convergent to infinity. Yeah? But it depends, and also it's a question what is the metric here. It's a more sophisticated example. Yeah? But generally speaking, in standard spaces like natural numbers or real numbers or rational numbers, infinity is not a number. So if a sequence goes to infinity, we say that it's not convergent at all. And just to give you another example of a sequence which is somehow convergent, but it's not. Let's say that an equals -1 to n, to the power of n. Okay? So how this sequence looks like? So a1 is minus 1 to the first, to the power of 1, right? So it's minus 1. a2 is minus 1 to the power of 2, so it's 1. It's minus 1 times minus 1, which is 1. Then a3 is minus 1 again. a3, a4, it's 1, etc. So you see that it is somehow stable, but there is no single number to which it converges. Because sometimes it's minus 1 and sometimes it's 1. What is important is the fact that it has two subsequences. It has a subsequence of this form, okay, which is convergent to 1, and it has a second subsequence of this form, which is convergent to minus 1. But the whole sequence is not convergent, right? Is it clear? Okay, and now we are ready to define what is a compact space. So let X be a topological space. We say that X is compact if for every sequence AN of the elements from the space there is a subsequence This means that we choose only some elements of this sequence. Like in the previous example, maybe every second element, or every third element, or 5th, 10th, and 20th, and so on, etc. But we choose only certain subsequence. There is a subsequence which is convergent to an element G from this space. Okay, so that's the definition. It's pretty abstract, but I know, for example, that Bartek used this notion of compactness in his PhD. So it's important to understand Bartek's PhD, for example.
But doesn't it only work for the spaces who have countable dense subspace?
To what's the question?
It only works for spaces who have countable dense subspaces, not generally, because you can have uncountable spaces which do not have countable dense subset, and you will not be able to reach some points in this way.
Yeah, then they are not compact.
No, but they may be compact.
No, if
Okay,
actually, that's just a definition. So
yeah, okay, but you gave the definition via sequences which are indexed by natural numbers only.
Yeah.
And to be honest,
you can define by filters and
or by nets. You
I know.
should take, any cardinal number. So this is the problem, because
that's true. That's true, but I don't want to complicate things too much. Yeah.
Yeah, but this is not. Then it is not a correct definition of compact space. We need to have a countable dense subspace in this space.
Yeah. Okay. Let's assume that. Okay. Yeah, but
I think so, but the problem is that you are indexing sequences by natural numbers.
I know.
If you take, for example, the first uncountable ordinal which is closed, and you will probably, it is compact, but
yeah, that's true. That's true. That's true. Yeah. So let's say that this is the definition for.
it is good for the reals, the space of reals, for example, like the subspaces of real numbers.
For every space with topological space with countable basis. Okay? So if we assume that our space has a countable basis, which is true, I believe, in all the cases you will consider in your life, then the definition is okay. Yeah? But if you yeah, you're right. Excuse me, you're right. If you consider some exotic, very big spaces, then yeah, you need a little bit different definition. But I want to go into technical details because then it will be even more difficult to understand. Yeah, so what is the intuition behind this, this definition? For example, if you have some examples, or maybe here. If you have a real line, for example, the question is if it is compact or if it's not compact. Yeah, so let's try to figure out if it's compact or not. If you consider a sequence of this type, like 1, 2, 3, just natural numbers. Yeah? Are you able to find a subsequence of this sequence which is convergent to a point from this space? Is there any subsequence of this sequence which is convergent?
1, 2, 3, 4, 4, 4, 4, 4. And
No, but with different elements, yeah, with different elements. No, I mean, no, but it's not a subsequence, no, because the sequence is like that, yeah. The sequence goes like that, A1 is 1, A2 is 2, A3 is 3, etc. Of course, if you have a sequence 1, 2, 3, 4, 4, 4, 4, 4, 4, 4, 4, then it's convergent to 4, right? But you have a sequence which is 1, 2, 2, 3, 4, 5, 6, 7, 8, and you cannot change that. You can only pick certain elements. Like you can say, for example, take 1, 2, 4, 7, 11, 12, etc. Is there any subsequence that is convergent? No, there is no. Which means that this space is not compact. That's a primitive test. Okay? And let's say we have a unit square, like here is 0, 1, 1, and it's closed. Is it compact or not? Yeah, that will be difficult. It might be difficult to prove. But yeah, the intuition is that if you take a sequence here, for example, you can take a sequence like this. Here, 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 here. And you can try to avoid any convergence. And I won't prove it here now, because it might be too difficult. But it won't be clear enough. But the intuition is that this space is so small and so bounded and closed that at a certain moment of time you won't be able to avoid these convergences that occur, and there will be some subsequence which will be convergent to a space, to a point from this space. So that's I cannot do it now, but actually this space is compact. This space is compact. And for example, such a space, let's say maybe this open disk. Open disk is not compact. Open disk is not. So in other words, the intuition is that compact spaces are spaces that are bounded and closed. This is the basic intuition. This is the notion that you are looking for. But in some exotic, in more exotic setting, not real line or real disk or real square, it's difficult to define this property just by saying that it has to be bounded and compact, bounded and closed. So we use this word, we use this notion of compactness, which defines this property using sequences, okay, and convergent subsequences. Okay. And I said that if we will have some time, I will show you one more example of interesting topological space that you maybe all know, but but maybe you have some questions to this. Okay, so just remember it and use it on reading markets PhD presentation. And now just final example of a so-called Cantor set. Yeah. So how we create Cantor set? We take a line. Let's say 0, 1. And we divide it into 3 parts, three parts, and then we remove this part. And then what we do next, we take this and we move this. And then you're in this position. And we continue. Yeah, and in the end, we get something which is a subset of the unit interval, but is very dispersed, so to speak. Is somehow nowhere dense. Yeah, I don't want to define that, but it's nowhere dense. And on the other hand, this set is uncountable. So there are more elements of this set than there are real numbers. Not real numbers, but rational numbers. There are more elements of this set than rational numbers. And that's a kind of more exotic space than those that we discussed. I mean, it's more exotic space, and it has more exotic properties than a real line or a real interval, and etc., etc. But at this moment, maybe I don't want to go into details because we have only.
Isn't it somehow related to the question I asked about defining with rational numbers, or the ones that are not rational numbers?
It's, I would say it's yet another story. It's yet another story. Yeah. Yeah, so we have 15 minutes left. So do you have any general questions or remarks? Because
I have a very general question. In the beginning you were talking about some topological is like a number of holes or number of nodes you didn't talk about, but it's also a topological property, the orientation and so on.
Yep.
And obviously they form some groups, like the number of holes. Is there any systematic theory about this group of features? Is there any number of such features, or is it infinite?
Features. Yeah, I would say that mathematicians, topologicians develop new features to distinguish certain spaces. And there are some standard features very often used from decades, I would say. And these features are like the number of holes, the number of connected components. So we were talking about connectedness and pathwise connectedness, and we said that the space can be connected or disconnected. When it's not connected, then it has so-called connected components. So, for example, if we have a space that looks like this, it consists of 3 balls. It has like 3 connected components. Every of these components is connected within itself, but the whole space is disconnected because it has 3 elements. And this thing, this number of connected components, is a topological invariant. So if you use a continuous mapping, then you won't lose you won't change this property. So as I said, so you have this number of holes, the number of connected components. You have compactness and other features which are classical, let's say, and that's one thing. And mathematicians study those properties and how they behave under various transformations. But on the other hand, sometimes you have like a given precise topological problem, like you have 2 spaces, for example, and you want to distinguish them somehow, and none of those standard features works. So, for example, they are both compact, both are not connected, they have many different features, but in all cases they are the same. But somehow you feel or you see that they are different. Like, for example, rational numbers and irrational numbers. For example, both are not compact, and etc., etc. Yeah, okay, there is a feature. Yeah, now I got it. Because these irrational numbers have uncountable number of connected components. Because every irrational number is a separate connected component. And rational numbers have countable number of connected components. Yeah? So that's a way in which you can distinguish it. But sometimes you can see the difference using the standard tools. And then often topologicians develop a new feature. They try to adjust to find a feature that will describe precisely the difference between the given 2 objects. Yeah? So that's how it works, and there is no finite catalog of this. There are some standards, but there are also...
Because, for example, groups are categorized. A few years ago it was finished, I believe, the number of groups.
Groups?
Finite groups. If they were counted, I don't know the exact number, but there was something like such a project.
Yeah, there is, I would say there is an infinite number of finite groups.
Or types of groups.
Finite simple groups.
Finite simple groups.
Yes, maybe, but some kind of this, and I wondered if there may be something like this in topology.
No, in some spaces you have catalogs of objects. Let's say, for example, you have a catalog of 2-dimensional compact objects in 3-dimensional space, for example. So if you think about 2-dimensional objects in 3-dimensional space, which are compact, then you have a catalog describing all types of those objects. relation to homeomorphisms. So not distinguishing them when they are homomorphic. But even in case of three-dimensional objects, it is too difficult. So there is, as far as I know at least, there is no closed catalog of three-dimensional objects in, for example, four-dimensional space. Recently there was this, the Poincaré hypothesis was proven by Perelman, like 10 years ago, and it gave us some answers, but it does not explain everything. Okay, any other questions or remarks? Yep.
You mentioned earlier that we could combine the sphere with the donut.
Yep.
I was wondering what kind of properties would this combined new topological space have? Would it be continuous? Because if it has a new hole, then it disrupts the continuity, wouldn't it? Or what kind of orientation would it have?
It depends in which way we glue them together, I would say. We can have a kind of disjoint sum, which means that we take one and we take two, we treat them separately, but in an abstract way we treat them separately. We don't glue them in a real space. And then we have like a space which has two connected components. Yeah, you cannot, when we have an insect moving in this space, you cannot take this insect cannot go from this space to the other, yeah, because there is like an ocean between those two parts. So it has two connected components. One is a sphere and one is a donut. So, for example, this one is not simply connected, which means that there are loops which are not contractible, and the other connected component is simply connected, which means that all the loops are contractible. So you have a certain type of a space that has certain topological features, and it can be distinguished from other objects by saying that it has two components. One component is simply connected, the second one is not simply connected. Both components are compact because both a tori and a sphere are connected, and that's how you can characterize it. Yeah? If you can also try to glue them in a different way, so you can sum them in a different way. For example, you don't want to treat them separately, but you can, for example, do it like that you take this sphere and you glue this tori somewhere here. Yeah, like this, for example. Yeah, you can create a space like this. So you have a sphere with a kind of tori emerging from this sphere. And then it has different topological properties. Like, for example, it is connected. Yeah, it is connected, though not simply connected still, but it has one connected component, etc., etc. And this space is different from the space which looks like this. Yeah? So this is one space, this is another space, and those two are different. So it somehow depends how you merge those two things. You can also create a Cartesian product of a donut and a sphere, and you will get yet another space with different properties. Okay, any other questions? Okay, so I guess, yeah, we are tired and we have 4 minutes left, but I guess we can finish now. And in case you have other questions, I guess I'll be here for another half an hour or maybe an hour, and you can approach me and I will be happy to answer other questions. So thanks a lot for your attention. And